If you're still measuring your flour by, just scooping a standard metal cup into a bag, you're already setting your cake up to fail.
Oh, absolutely.
I mean, your measuring cup is essentially lying to you.
It really is.
So welcome to the deep dive. Today we're exploring why abandoning volume for mass is really the only way to master the chemistry of the kitchen. We are unpacking this really fascinating set of guidelines from a source text, and it's focusing on Unit 2, which is tools and equipment for baking.
Right, the essential toolkit.
Yeah, and what's brilliant about this material is that it doesn't just hand us like a random shopping list of spatulas and pans.
No, it doesn't.
It hits us with this core philosophy right away.
Yeah.
And that philosophy is baking is chemistry.
Yeah.
So, okay, let's unpack this, because for most of us, cooking dinner is kind of like playing jazz, right?
Oh, for sure. Very improvisational.
Exactly. You throw a handful of herbs in a pot, you adjust on the fly, you taste it, you add
A
salt.
little this, a little that.
Right. But baking is, it's like building a suspension bridge.
That is a great way to put it.
Because if your math is wrong, or, your materials just lack structural integrity, the entire thing just collapses under its own weight.
It collapses completely. Yeah, it requires an entirely different mental framework.
Yeah.
And what's fascinating here is how the text immediately links the concept of accurate measurement directly to the promise of perfect results.
Perfect results, yeah.
It establishes this really rigorous scientific gut line right from the jump. Like, we aren't just in a kitchen anymore.
Right.
We are in a laboratory setting.
A lab, yeah, exactly.
The ingredients, your flour, your sugar, your leavening agents, they are reactive chemicals.
Right, they're not just food.
Exactly. And if you want the reaction to yield this beautifully aerated crumb instead of, well, a dense gelatinous brick.
Which we've all made at some point.
Oh, yes, we have. But if you want to avoid that, you have to respect the physical properties of those chemicals.
Okay, so that means utilizing specific tools, right? Tools engineered to control and monitor that reaction from the very first step.
Exactly. Which brings us right back to that measuring cup problem you mentioned.
Yeah. Let's look at the measuring tools listed in our source, because we have measuring cups, measuring spoons, and a digital scale. But to me, there's a glaring conflict here.
How so?
Well, the text dictates that accurate measurement equals perfect results, right?
Right.
But volume measurements, like cups and spoons, they're inherently inaccurate. I want to push back on this a little, because if I have cups and spoons, is a digital scale truly necessary for a home baker?
Oh, yes.
Or is it just a fancy gadget? Because, a cup of compacted flour sitting at the bottom of a pantry bin, that can weigh like 30 to 40 grams more than a cup of freshly sifted flour.
Exactly. And that is why the digital scale is really the only tool on this list that actually fulfills the text's core philosophy.
Okay, so the scale is the truth teller here.
Precisely. The digital scale eliminates the variables of bulk density and, well, human error.
Because we all scoop differently.
We do. Flour is highly compressible and sugar is hygroscopic, which means it absorbs moisture from the air.
Oh, wow.
So on a humid day, a cup of sugar physically behaves differently than on a dry day.
That makes so much sense.
Yeah, volume measurements just fail to account for those environmental shifts. But mass, weight, that is absolute.
Right, 120 grams is 120 grams.
Exactly 120 grams, regardless of how tightly packed it was in the bag or what the humidity is doing outside.
So by shifting from volume to mass with a digital scale, you're locking in the baker's percentages.
You ensure the ratio of hydration to starch to fat remains exactly as the chemical formula intended.
Okay, so we've achieved absolute precision on the digital scale. We're scientists now.
We are.
But that math is completely useless if we don't protect those ratios during the mixing phase. Right?
Oh, absolutely.
So let's look at the mechanics of the mixing process. The text provides a very specific arsenal for this.
Yes, it does.
We've got a whisk, a hand mixer, a wooden spoon, a rubber spatula, and mixing bowls. And here's where it gets really interesting, because what stands out to me is the deliberate designation of materials.
Right, it's very specific.
Yeah, it doesn't just say spoon or spatula. It specifies a wooden spoon and a rubber spatula.
Yes.
So from a chemistry perspective, this indicates we're dealing with like thermal conductivity and fluid dynamics, right?
Right.
Why wouldn't it just be a metal spoon?
Well, if we connect this to the bigger picture, the agitation phase isn't just about making a homogeneous paste. You are fundamentally altering the physical state of the ingredients. And you need tools with specific mechanical properties to do that without ruining the baseline math you just established on your scale.
Because if you ruin the map, the bridge collapses.
Exactly. Let's look at the hand mixer and whisk first.
Right.
These are designed for rapid mechanical aeration.
So beating air into the batter.
Yeah. When you cream butter and sugar together or whip egg whites, you're using shear force to unravel protein structures and trap these tiny micro bubbles of air.
Wow, okay.
You're building a delicate foam matrix that will expand later under heat.
And a spoon just can't do that.
A regular spoon simply cannot generate the necessary shear force or velocity to create that matrix.
Right. But the wooden spoon is on the list for a completely different reason, isn't it?
Yes.
Because wood is an incredible thermal insulator.
Exactly.
Like, if you are mixing a highly dense, heavy dough, a metal spoon can just bend under the torque, first of all.
Oh, yeah.
But more importantly, a metal spoon conducts heat.
Which is dangerous for baking.
Yeah. If you are incorporating ingredients over a double boiler, or if you're working with a temperature-sensitive dough, where you don't want the ambient heat of your hand transferring into the butter and melting it prematurely.
Yes.
The wooden spoon acts as a thermal barrier. It gives you this massive tensile strength without altering the temperature of the reaction.
It really is the ultimate temperature-neutral workhorse in the kitchen.
That's a great way to describe it.
But then you have the inclusion of the rubber spatula.
The rubber spatula.
Yeah, often referred to in professional kitchens as just a scraper. And this is arguably the most critical tool for preserving your scale's accuracy.
Wait, really? The spatula?
Yes. Think about the viscosity of cake batter. When you mix it in a bowl, a really significant percentage of that carefully weighed hydration fat matrix clings to the curved sides of the bowl.
Oh, yeah. It coats the whole inside.
Right.
And if you use a rigid wooden spoon to transfer that batter into your baking tin, you are leaving a substantial margin of your formula behind.
Exactly.
You're essentially abandoning the precision you just fought so hard for on the digital scale.
Which defeats the whole purpose. The flexible edge of a silicone or rubber spatula, it conforms perfectly to the geometry of the mixing bowl.
So it gets everything.
It allows you to scrape the vessel entirely clean. It acts as the guardian of your ratios, basically.
Guardian of the ratios. Love that.
It ensures that the exact mathematical equation you built on the scale is the exact equation that goes into the oven.
Because without it, your hydration levels drop.
Right, your leavening ratios skew, and the final structural integrity of the bake is compromised.
It is so brilliant how these tools function as a system of checks and balances.
It really is.
Okay, so we measured with total precision, we've agitated to build our internal structures, and we've scraped every last drop into our vessel.
Ready for the heat.
Exactly. Now, that batter needs a controlled environment to undergo its phase change. So moving from agitation to thermal transformation, the source material lists our baking tools.
Let's hear them.
We've got cake tins, cookie trays, a muffin pan, parchment paper, and a cooling rack.
Okay.
Now, obviously, the tins and trays provide the physical boundaries for the batter as it expands.
Right, they shape the outcome.
But looking at this through our chemistry lens, the parchment paper is functioning as a crucial thermal barrier. I mean, it's essentially an insurance policy against permanent molecular bonding.
That is exactly what it is.
Yeah.
Because as the batter hits high temperatures in the oven, these complex reactions occur right at the boundaries where the batter meets the metal tin.
Okay.
You have the Maillard reaction, you have caramelization of sugars, and the rapid coagulation of proteins.
A lot of science happening.
A lot of science. And metal is highly conductive. So without a release agent, those coagulating proteins will literally bond with the microscopic pores of the metal cake tin.
Oh, wow. Which means your perfectly engineered cake just tears itself apart when you try to extract it.
It's a disaster. Yeah.
So the parchment paper, which is, typically treated with this ultra-thin layer of silicone, provides a non-reactive, non-stick barrier.
Exactly.
And that ensures the chemical structure remains intact when you remove it. But here's the thing that really caught my eye. The cooling rack is grouped under baking tools.
Yes.
I love this classification because it acknowledges that the baking process does not end when you cut the heat.
Not at all.
Like, I look at the cooling rack like a runway after a long flight.
Yeah. That's a perfect analogy.
The heat is off, the pan is out of the oven, but the thermodynamic process is still incredibly active.
Highly active.
Because if you leave it in the pan, it's just going to sweat.
Yes. It is a critical phase of the chemical reaction. When you pull a baked good out of the oven, its internal structure is still remarkably fragile.
Oh, really?
Yeah. The starches have absorbed water and swelled a process called gelatinization, but they haven't fully set yet. The proteins are still firming up,
Yeah.
and the moisture inside is still in the form of vaporized steam.
Oh, I see.
So if you leave a cake sitting in its metal tin, the high thermal mass of the metal will continue to conduct heat right into the edges, and you'll end up over-baking the crust.
And if you just flip it out directly onto like a solid granite countertop, all that internal steam trying to escape from the bottom hits an impermeable cool surface.
Yes.
And it immediately condenses back into liquid water.
Resulting in a soggy, compromised base. Nobody wants that.
So everybody wants a soggy bottom.
Yeah.
So the cooling rack is a thermodynamic regulator.
Exactly. By elevating the bake, it allows 360-degree ambient airflow.
Right.
It stops the conductive cooking process of the pan while allowing the latent steam to dissipate evenly.
So this controlled deceleration of heat is what finally locks the starches into their permanent, rigid structure without introducing excess moisture.
Exactly. The flight truly isn't over until the internal temperature stabilizes on that wire rack.
That fundamentally changes how you view a simple wire grid. I mean, it's not just a shelf. It's a vital piece of structural engineering equipment.
It really is.
So our reaction's complete. The starches have gelatinized, the structure is locked in on the cooling rack, and the internal temperature is finally stabilized.
We're ready for the next phase.
Right. Now, the protocol shifts.
Yeah.
We move out of the thermal phase and into the realm of structural aesthetics.
Yes.
The text introduces the decoration tools. It lists piping bags, nozzles, and it specifically highlights round, star, and leaf variety scrapers, and a turntable. And when I look at this list, my mind immediately jumps to, like, masonry or industrial lathe work.
Because the underlying mechanics are exactly the same.
It's crazy.
This raises an important question, actually, about how we view this stage. We have a tendency to separate the baking from the decorating, right?
Yeah, for sure.
Viewing the former as rigorous science and the latter as this free-form subjective art.
Like we can just play around now.
Exactly. But the tool specified here proved that the demand for precision doesn't evaporate just because the heat is off. Take the turntable and the scrapers.
Okay.
When you place a tiered cake on a spinning turntable and apply a rigid scraper against its side, you are utilizing rotational symmetry.
You are literally doing lathe work with buttercream.
You really are.
You're applying shear stress to a fattened sugar matrix to create an aerodynamically smooth, perfectly level surface.
Exactly. Buttercream exhibits non-Newtonian properties.
Oh.
Its viscosity actually changes under shear stress. So the scraper aligns that matrix, creating a structurally sound barrier that seals in the cake's internal moisture while providing this mathematically perfect cylinder.
And that precision extends directly to the nozzles, too.
Yes, it does.
Because the text goes out of its way to specifically name round, star, and leaf nozzles.
Mm-hmm.
It doesn't just say decorating tips. It treats them like highly specialized extruders, which is exactly what they are.
Precisely.
I mean, you can't just forcefully eject frosting out of a cut plastic bag and expect it to hold a complex shape.
No, you can't.
The nozzle dictates the flow rate and the surface area of the extrusion.
It really does. And this is where texture and flavor perception are manipulated through structural design.
Oh, really? Texture, too?
Yeah. When you apply pressure to the piping bag, the frosting is forced through a highly specific aperture. So a round nozzle extrudes a smooth structural cylinder.
Like for writing letters or making dots?
Exactly, often used for load-bearing borders or precise text. But a star nozzle is a brilliant piece of engineering.
How so?
Well, by forcing the frosting through serrated teeth, it exponentially increases the surface area of the extrusion.
Which means more surface area is exposed to the air.
Yes.
And that alters the way the frosting sets, and it changes the way it collapses on the palate when you eat it.
Exactly. It creates ridges that catch light for visual volume, but it also alters the mouthfeel entirely without adding any additional weight to the cake.
That is fascinating.
And then a leaf nozzle utilizes a specialized V-shaped aperture.
Oh, right.
That manipulates the fluid dynamics of the frosting, forcing it to fan outward under pressure and taper to a micro-thin edge when the pressure is released.
Wow. So the text highlights these three specific nozzles because they represent the controlled, repeatable application of physics to aesthetics.
Yes. Even the art is strictly governed by fluid dynamics and structural engineering.
The medium just changes from a liquid batter to a semi-solid frosting.
But the physics remain absolute.
All right, so to bring this entire operation together, we have to examine the engine powering this laboratory.
The heat source.
Yes. We have our ingredients meticulously weighed by mass, mechanically agitated to denature proteins, shaped, stabilized on thermodynamic racks, and extruded through engineered nozzles.
A lot of work.
A lot of work. But none of this complex chemistry initiates without the ultimate catalyst, which is heat.
Right.
So the text lists our heat equipment with some fascinating caveats. It lists a gas stove, an oven, but with the caveat if available, and pressure pot baking, with the caveat if no oven.
Yes.
Now, the oven and the gas stove are standard, but so what does this all mean when we zero in on pressure pot baking?
It's so interesting.
To me, this represents a massive democratization of culinary science.
It is perhaps the most profound takeaway from the entire source text, really.
Yeah.
By explicitly outlining pressure pot baking if no oven, the material shatters the illusion that scientific rigor requires expensive, specialized architecture.
You don't need a fancy kitchen.
Exactly. Let's look at the physics of a traditional oven. It is fundamentally a dry, insulated enclosure that maintains a steady ambient temperature.
Okay.
It utilizes convection and radiant heat to penetrate the batter evenly from all 360 degrees.
Which triggers the leavening agents, causes the moisture to convert to steam, and ultimately cooks the batter.
Yes. Now, consider a heavy-duty pressure pot.
Okay, I'm with you.
If you remove the pressure valve so that the steam can freely escape.
So it doesn't explode.
Exactly, preventing the interior from becoming a wet, pressurized environment. And you place a small wire trivet inside to elevate your cake tin off the direct conductive heat of the bottom floor.
Right, so it's not touching the bottom.
You have engineered a localized thermodynamic envelope.
You've basically created a miniature oven cavity on a stovetop.
Precisely. You place that pot over a gas stove flame.
Okay.
The thick metal walls of the pressure pot absorb the extreme localized heat from the burner, and they radiate it evenly throughout the enclosed space of the pot.
Wow. And the trivet prevents the bottom of the cake from scooching via direct conduction.
Exactly. It forces the batter to bake via the ambient radiant heat trapped under the lid.
It functions almost exactly like a cast iron Dutch oven over a campfire.
Yes, very similar principle.
That is amazing. Because the chemical compounds in the flour and the leavening agents, they don't have eyes.
No, they don't.
They do not know and they do not care whether the ambient thermal energy triggering their phase change is being generated by a $5,000 imported electric wall oven or a heavy metal pot sitting over a basic gas flame.
The chemistry remains true regardless.
Yeah, so cool.
As long as you, the operator, understand the principles of heat transfer, conductive versus radiant heat, and you can manipulate the environment to maintain that 360-degree thermal envelope, the reaction will execute perfectly.
It just strips away every excuse.
It really does.
It proves that the magic isn't housed in the high-end kitchen appliances. The magic is entirely in understanding the scientific process.
Which is exactly what the text is trying to teach us.
It all circles back to the text opening philosophy. Baking is chemistry.
It is.
When we look back at the journey we've just mapped out, from the absolute, uncompromising mass calculations of the digital scale, through the sheer force mechanics of the mixing tools, past the thermodynamic runway of the cooling rack, all the way to the ingenious thermal envelope of the pressure pot. It all comes down to intentionality.
Intentionality and a deep respect for the physical laws governing the ingredients.
Yeah.
Grasping these concepts transforms you from a passive participant who, just blindly follows instructions and hopes for the best into an active kitchen scientist.
I love that. Kitchen scientist.
When you fundamentally understand why a flexible rubber scraper preserves your hydration ratios, or why a cooling rack prevents starch retrogradation from ruining your crumb structure, you take total control of the elements.
You're not just hoping it works out.
No, you are orchestrating a highly controlled, repeatable scientific outcome.
It completely reframes what it means to step into a kitchen.
It really does.
But, as we wrap up this deep dive into the mechanics of baking, it does leave me with one lingering, slightly philosophical question for all of us to chew on.
Oh, what's that?
Well, if the source material is absolutely correct, if baking is purely chemistry, where utilizing the exact tools for accurate mass measurement and controlled thermal reactions guarantees a perfect structural result, what happens to the romance of the secret family recipe?
Oh, that's a good question.
Right. Is the legendary magic of a grandmother's famous cake just a hidden, highly precise mathematical formula that we could replicate flawlessly with a digital scale and a makeshift pressure pot oven?
It might be.
Or Is there some unmeasurable human element, some subtle variation in the biological jazz of it all, that none of our rubber scrapers, structural nozzles, or thermodynamic formulas can ever truly capture?
That is fascinating.
Just something to think about next time you step into the lab.